However, we still have to compute for the value for A. So, how to compute, what is the equation for A? The equation for A is this. So for stage 1, the value for A, no. The value for A1 can be computed by this equation. L naught and B1 has already been given to the problem or derived by Mr. Serrano earlier. You might be wondering what is this? Earlier we said that the equilibrium relation is YA is equals to 2.53 XA. So 2.53 is the slope of that equation. For stage N, the equation for A is also, this equation has been derived earlier or given to the problem. As you can see, why did I get two equations for A? So, Mr. Alejandro earlier said that A is constant. It is not constant, but it is a constant. So we need to know if the value of A is constant or not. So I derived two equations for A. So as you can see, it is not constant. So we need to get the geometric average for A. Yan, pray ko na. So getting the geometric average, plugging in all the values to our Bremser equation, we should obtain number of 5.04 stages, which compares closely to the 5.2 stages obtained earlier using the graphical method. So, classmates, that's how we did that. So, for the third problem, here is Miss Isabel Gutierrez.
Now we are on to our last problem, discussing interface compositions in interface mass transfer. The solute A is being absorbed from a gas mixture of A and B in a wetted wall tower with the liquid flowing as a film downward along the wall. At a certain point in the tower, the bulk gas concentration is 0.38 mole fraction and the bulk liquid concentration is 0.1. The tower is operating at 298 Kelvin and 1.013 times 10 to the 5 Pascal. And the equilibrium data are as follows. Next slide. There. The solute A diffuses through stagnant B in the gas phase and then through a non-diffusing liquid. With this equation, we know that we are dealing with DTSM. Next slide. Using the correlations for the lead solutions in wetted wall towers, the film mass transfer coefficient for A in the gas phase is predicted as 1.465 times 10 to the minus 3 kilogram mole A per second meter squared mole fraction. And for the liquid phase as 1.967 times 10 to the minus 3 kilogram mole A per second meter squared mole fraction. We need to calculate the interface concentrations YAI and XAI and the flux NA. Next slide. For the solutions, as Ms. Garing have stated, since the correlations for the dilute solutions 1 minus YAIIM and 1 minus XAIIM are approximately 1 and the coefficients are the same as K prime Y and K prime X, the equilibrium data are plotted in the figure below. Point P is plotted at YAG is equal to 0.38 and XAL is 0.1. Next slide. There. We should plot P around 1 and 0.38. There. For the first trial, as I have stated earlier, 1 minus XAI M and 1 minus YAIM are assumed as 1. You need to get the slope. Using the equation Ms. Garing have stated earlier, we know what K prime X and K prime Y are, and we for the first trial we assume that 1 minus XA and 1 minus Y is equal to 1. So putting it in the equation, there we have a slope of negative 1.342. Next slide, please. A line through point P with a slope of negative 1.342 is plotted in the graph intersecting the equilibrium line at MI. There. In here, we get YAI is equal to 0.183 and XAI is equal to 0.247. Next slide, please. For the second trial, we use YAI and XAI from the first trial to calculate the new slope. We get now 1 minus YAI, next slide please, and 1 minus XAI, next slide, and we plug it here in this equation again to get a slope of negative 1.163. The slope earlier was computed as negative 1.342, which is far from negative 1.6163. So we need to do another trial. Now next, using the new slope, we again draw a line passing through point P with a slope negative 1.163 and it intersects at YAI is equal to 0.197 and XAI is equal to 0.257. Now we need to calculate for the slope again. Next one. We need to get 1 minus YAI and 1 minus XAI. And we plug it in again in this equation. There. Now we get negative 1.160 which is essentially the same as the slope of negative 1.163 for the second trial. Hence, the values for YAI is 0.197 and XAI is to be 0.257 and that's shown as point M. Next slide. Now, we need to calculate the flux. The flux, as Ms. Gary has stated earlier, is equal to the K prime Y over 1 minus YAIM times YAG minus YAI. Now we plug in the values and we get the flux 3.78 times 10 to the minus 4 kilogram mole per second meter squared. Another equation for the NA is, for the flux rather, is K prime X over 1 minus XAIM times XAI minus XAL. Plugging in the values, we get the answer 3.78 times 10 to the minus 4 kilogram mole per second meter squared. Note that the flux NA through each phase is the same as in other phase, which should be the case as steady state. Next slide. This is the graph. Now, to wrap things for our discussion, we have Mr. Serrano.
Hello again. To summarize all the points in our report, gas absorption is basically a separation process wherein a liquid and a vapor stream comes contact on equilibrium stage. And then, for the purpose of solving one of the soluble components in the gas, the liquid. So in getting the before the equilibrium stage is obtained, there is interface mass transfer. So in calculating the mass transfer mass flux rather, we have presented to you the film theories. Okay. In calculating for the total number of equilibrium stages, we have to plot the equilibrium line. The equilibrium line is plotted using Henry's law or other equilibrium data obtained from handbooks, for example. And then the operating line is plotted using the operating conditions of the tower, such as molar flow rate, so on and so forth. And then for the graphical approach, we start from the coordinate of XA0, YN is 1, or the top of the tower, and then staging off and counting the total number of horizontal lines. And then if you don't want to use the graphical method, use the transfer equation. And that concludes our report. And then,
We would like to thank our classmates, especially those who supported us. Thank you, classmates. We owe it to you.
Also, hope you liked our lecture, hope you enjoyed, and hope you learned a lot. Thank you very much. And here ends our report.
Thank you.
Thank you.